Good morning, everyone. Today I'm going to talk about how we study critical gauge theories on the fuzzy sphere. I will especially talk about how we approach Chern-Simons matter theories with the help of nonlinear sigma model. And so this talk will mainly be based on this first paper with my supervisor Zheng He and some upcoming works. I will also briefly highlight some of our other progress on the fuzzy sphere. So as a brief introduction, critical gauge theories is one of the few known ways to construct interacting 3D CFTs. It is also the description of many exotic critical phases and phase transitions in the infrared. As a well-known example, the SO5 deconfined criticality, it is described by the scalar QED with two flavors of bosons, or QED with two flavors of fermions coupled to the Grassmannians-Yukawa interaction, or the SU2 QCD with two flavors of fermions. Here, by gauge theory description, I don't mean that microscopically there exists a gauge field structure in the microscopic model, but rather the lattice model, for example, that realizes the SO5 D2CP. And the gauge theory Lagrangians, they flow to the same infrared. So when I'm talking about constructing gauge theories, I'm using the term in the same sense. We're not constructing the gauge fields themselves, but rather the fuzzy sphere model and the Lagrangians, they flow to the same IR. And so similarly, the O4 D2CP is described by the QED with two flavors of fermions, and the Dirac spin liquid is described by the QED with four flavors of fermions. However, obtaining the critical data of these critical gauge theories is difficult. We even don't know the nature of many gauge theories. For example, there is this famous conformal window problem. That is to say, given a gauge field, if you couple it to some number of flavors, when the number of flavors fall into a certain window, it flows to a conformal fixed point. But where is that window? It is largely an unknown problem. And so Johannes will talk about this in more detail in the afternoon. So to make things even more interesting, we can add some non-trivial dynamics to the gauge field. That is to say, for example, the Chern-Simons terms. And coupling the matter to a Chern-Simons theory will give us the Chern-Simons matter theory. And such theories bear theoretical significance because first, it can describe transitions between topological orders. They can also host duality between different interacting theories. And with the development of recent moiré material, it is very much it's experimentally relevant. However, obtaining their critical data is even more difficult. For example, for conformal bootstrap, it has difficulty distinguishing theories with the same global symmetry. And for Monte Carlo, such parity breaking theories can often result in a sign problem. As a result, even one of the simplest theories, for example, even if the simplest theories, for example, U1 level 2 coupled to one level of boson, its critical data is unknown. Well, until this summer. Yes, so continuing, we want to put those critical gauge theories on the fuzzy sphere. This is also quite a difficult task to do, as we need to construct a fuzzy sphere model that very naturally allow the critical gauge theories to emerge from it. That is to say, the model has to have correct symmetry, correct anomaly, and maybe the correct phase diagram. So to address this task, we use an intermediate step of nonlinear sigma model coupled with a Wess-Zumino-Witten term. That is to say, we first match the fuzzy sphere model with the nonlinear sigma model with Wess-Zumino-Witten term, and then to match the nonlinear sigma model with the critical gauge theories. So what do we mean by matching critical theories with nonlinear sigma model? In 2D, the scenario is rather simple because the Wess-Zumino-Witten term is relevant, and starting from a free theory, it will automatically flow to the well-known Wess-Zumino-Witten CFTs. But in 3D, the scenario is a little bit different, as the only fixed point in the renormalizable region of the nonlinear sigma model is the symmetry-broken fixed point. But if we go away from the renormalizable region, we hit it with a finite coupling, just like what we do in microscopic models or lattice models. We can put the SSB into a phase diagram. And the phase diagram typically look like this. So adding finite interaction, you will hit a repulsive fixed point, and on the other side, it will flow to another stable fixed point. It is possible that these two fixed points both correspond to some kind of CFTs. It is also possible that the repulsive fixed point corresponds to a CFT, and the attractive fixed point corresponds to some kind of gap phase, for example, the topological order. So these CFTs and the nonlinear sigma model, they have the corresponding symmetry and anomaly. So that's the sense we say that they are matched. So as a most familiar example is that the SO5 deconfined criticality, it is matched with the nonlinear sigma model on a fourth sphere with a Wess-Zumino-Witten term. So the fourth sphere essentially describes the 5-dimensional order parameter, and the Wess-Zumino-Witten term captures the anomaly, namely the U1 flux captures a SO3 spin half. So how do we put this model?
Can you say a bit more about this anomaly? What exactly?
It's
exactly this anomaly that you need to match. What is the precise calculation that is? Supposedly some Hopf anomaly, but what is it?
Yes. So for example here it's for example in this case the anomaly of the determined criticality is the W4 of SO5, which.
But it's anomaly of what? Of which symmetry?
Of the SO5 global symmetry. Okay. Yeah. Okay. So shall I continue?
Yeah.
Okay. Okay. So how do I put this nonlinear sigma model on the fuzzy sphere? Let us recap it from a new perspective. So we notice that this fourth sphere, S4, can be written in terms of a Grassmannian, SP2 over SP1 times SP1. Here we use a notation such that SP1 equals SU2. So what does this Grassmannian essentially tells us? It tells us that we should put 4 flavors on the fuzzy sphere, and the four flavors can have a global symmetry of SP2, which is a subgroup of SU4.
But that's just SO5 divided by SO4.
Yes, exactly. But written in this form will make things on the fuzzy sphere somewhat easier.
Okay.
Yeah, but it is essentially the upside is SO5 and the downside is O4, SO4. Yeah, so we half fill it. So the symmetry breaking pattern is to fill 2 flavors and leave 2 flavors empty. So the 2 filled flavors will have a remaining symmetry of SP1 or SU2, and the other 2 empty flavors will have a remaining symmetry SP1. So that this symmetry breaking pattern is described by the symmetry breaking from SP2 to SP1 times SP1. Hence, SP2 with SP1 times SP1 projected. So here we can consider a even more general case. That is to say, we generalize this S4 as a symplectic Grassmannian into a general Grassmannian, and the Grassmannian of either symplectic group or U or SO. So we know that these theories can host a lot of critical gauge theories, namely Chern-Simons matter theories. So here we look at the most familiar example of the U Grassmannian coupled to the nonlinear symmetry model on the U Grassmannian coupled to a Wess-Zumino-Witten level K. So this can correspond to the bosonic theories. For example, the UM level K coupled to n flavors of bosons, or UN minus M level minus K with n flavors of bosons. So this describes the phase transition between the symmetry broken phase and which is the renormalizable fixed point of the nonlinear sigma model, and the topological orders UM level K or UN minus M level minus K. So this exactly looked like the phase diagram that I showed before. So alternatively, we can have the phase transition between those 2 topological orders, which is the SUK level half n minus m coupled to n flavors of Dirac fermions. This fixed point is separated from the SSB by a multi-critical point.
Sorry, so which of these fixed points are described by that theory on top?
All of those. So you can regard the
blue ones and not the red one, though.
The red one as well, but you can say it's much more difficult because it is a multi-critical point. Mm-hmm. It can flow in this direction to the SSB, and the critical points. It can also flow to the topological orders. So it's more difficult. Yeah. So you can essentially regard this kind of nonlinear symmetry model as a lattice model where we can have many parameters to tune, and by tuning them, you can reach different fixed points. Yes.
Just understand, when you say bosonic theories or fermionic theories, you don't. All of these, the sigma model has no neutral fermions, right? The distinction is just whether they're bosonic or fermionic matter.
No. The only difference is we write them in terms of bosonic or fermionic matter. And if it is a CFT, then the CFT content would all be bosonic. Yeah. Yes.
Not necessary, right?
Yeah. When k is even.
Okay.
Yes.
So you're saying if you take the thing at the top and you regularize it, and you have one coupling constant, as a function of the coupling constant, it could be any of these possibilities? Or?
Yes.
Okay.
Yes.
How do you distinguish bosonic and fermionic theories by looking at defects or something else?
So you want to look at the defect of these theories?
Yes. Or are they duals? Or are they really distinguished? Or
I would say maybe their defects could be different if you look at their, for example, Wilson line and
stuff like that.
Yeah, but we haven't looked into them in more detail. The bulk themselves are even not clear enough, so it is a bit too ambitious to think about the defects. Yeah, of course, these field theories are quite complicated. So in the following parts of my talk, I will talk about another simpler example of a new series of symplectic CFTs that we have found, which which is derived from the symplectic Grassmannian nonlinear signal model. After covering this concrete example, I will talk more on how the fuzzy sphere, how the nonlinear signal model bridges fuzzy sphere and its IR fate. Namely, how exactly do you match fuzzy sphere with nonlinear signal model, and how exactly do you match nonlinear signal model with the critical theories. And since it's the last day of the conference, if time allows, I will also briefly highlight some of our other progress on the fuzzy sphere, like for defects and boundaries. So our target is to generalize this D2CP into a general symplectic Grassmannian nonlinear signal model with Wess-Zumino-Witten level 1, SPn over SPm and times SPn minus m. And this nonlinear signal model has several candidate Lagrangian theories. For example, there is the SPm level 1 or SPn minus m level minus 1 coupled to n flavors of bosons in the fundamental wrap of the symplectic group. Or there can be n flavors of Dirac fermions in the fundamental wrap of SPn that is coupled to SU2 with some Chern-Simons level. So how do we put this thing on the fuzzy sphere? It is pretty similar to how we put the D2CP on the fuzzy sphere. So we first need 2n flavors of fermions on each orbital, they can have a maximal symmetry, flavor symmetry of SU2n. We then break the symmetry to SPn. And the symmetry breaking pattern tell us to put fill 2n flavors out of the 2n flavors, so that the symmetry broken phase could have a remaining symmetry of SPm times SPn minus m. So we put 2n flavors on each orbital. We break the symmetry from SU2n to SPn, and we assign a filling of 2m out of 2n.
But in fact, this is just a filling fraction.
Yes.
You don't fill just 2m flavors. You fill all of them.
Yeah. Yes. So that this allows us to have a most natural symmetry breaking scenario, which is on this nonlinear signal model. Thank you for helping me. Yes.
So
yes.
Does it become more complicated when you're away from half filling, or you don't have any issues?
We don't have any issues, but I would say many other algorithms could have issues. So that's the strong point of ours.
Do you impose this 2m out of 2n on average across the whole system, or for each orbital?
On average, so we allow hopping from flavor to flavor. So it's just a overall filling of n over m over n. Okay, shall I continue? Okay. So a brief recap. We have 2n flavors of SPn fundamental. So we need to construct the Hamiltonian with the correct symmetry. So the simplest construction would be to make use of the fermion bilinears, local fermion bilinears. For example, there can be the density operator psi dagger psi at some r, which is 2n SU2n invariant. There can also be a pair operator, psi transpose omega psi, which is SPn invariant, but not SU2n invariant. So in the Hamiltonian, we can put local density-density interaction and the local pair-pair interaction. The first term preserves SU2n, and the second term breaks SU2n to SPn. In fact, we can generalize this local interaction to some pseudo-potentials. And in our simulation, we actually put 5 parameters. That is to say, the U pseudo-potential 0, 1, and 2, and the V pseudopotential 0 and 2. And with these tuning parameters, we are able to find the best point with the conformal symmetry and diagnose the CFT corresponding. So remind you that to extract the conformal data, we make use of the state operator correspondence, namely the information of the operator. For example, the spin and the SPN rep can be measured from the data of the state. And at half filling, there's an additional parity symmetry, which is applied as the particle Hall transformation. And more importantly, the slitting dimension is read out from multiplying the excited energy with a factor, and yes.
But you're not working on half filling, right? Or are you?
We are working on general filling.
Like n over n, or m over n.
Yeah, general m over n.
So you don't have parity.
I will show an example. For example, we studied the SP4 at half filling. That is with parity.
But for the other examples, parity is emergent in the IR.
No, the CFTs we want to study, they don't have parity. So the Chern-Simons matter theories, for example, they automatically break parity. Okay. Yes. So we search for the best point that meets the criteria for the conformal symmetry, namely the conserved currents and the integer-spaced multiplet. So I'm going to show you some results in favor of the conformal symmetry. So so for each n and m, we are able to categorize the operator spectrum into conformal multiplets, and each multiplet consists of a primary and the descendants of their primary. So you can see, for example, this is the lowest lying operator with SP3 with 1/3 filling, and you can see that there is a primary, and we can find all of its descendants below, for example, below 6, and they are very close to integer spacing. And for the conserved symmetry current, that is to say, it has spin 1 and sits at 2. We can look for all its descendants with or without the epsilon structure. And we do this for slightly higher operators. It is also close to perfect. And there's also the SP4 theory, and we can do the same thing. Yes?
And this 7654, that's the number of orbitals?
Yes, that's the number of orbitals. Yeah. So this is the maximal size we can reach. You can see if you have 7 orbitals, you already have 42 sites. So that's quite close to the limitation of exact diagonalization. Yes. So how exactly do we know that those states with integer spacing, they are the descendants of the same primary? That is when we make use of the conformal generator.
Yes. The filling was the one on the right. That would be the SP4 at a quarter filling.
Yes. Yes.
Cool.
So the filling is m over n. Yes.
So this is in some region of V over U, is that?
Yes. This is a very fine-tuned point. I will show later how we fine-tune it. Yeah. It's not clear whether or not it's stable.
Okay.
Yes.
So when you have a quarter filling, you have an insulating state. Or you think, is it a metal? Is it a what type of what is the ground? I don't understand.
By insulating, you mean charge gap, or? Yeah. Everything here is charge gapped, so that the CFT degree of freedom is separated from the charge degree of freedom. So everything is insulating in that sense, I would say.
So you can also say it's integer filling. You can also say the integer filling is like 1 particle per orbital.
And you don't do n equals m equals 2?
N equals m equals
I guess 2. SP4 goes to SP2 times SP2. Or
yeah, yes, we have done that, but it's just not enough space to show here. Yeah, I will show some results of SP4 with half filling, which is quite important because it corresponds to the SU2 QCD. Yes, I think for the half-filled case, Johannes will talk about it more when we are studying it with quantum Monte Carlo.
I see.
Here we just focus on some small n's. Okay. Shall I continue? Yes. So we make use of the conformal generators, which I think it's already been covered on Monday by some very nice work. And if you integrate the Hamiltonian density with the coordinate, you get the conformal generator P plus K, which increase or decrease the number of partial derivatives by 1. So for example, if you add it on phi, you get partial phi. If you add on partial phi and you project it to L equals 0 sector, you get a linear combination of phi and Bot's phi. And similarly, to L equals to 2 sector, you get partial phi. So we add the conformal generator on each of these states and take the overlap with the states that we are expected to see. So in theory, these kind of overlaps should be 1. So closer to 1, that means the quality of the conformal multiplets is better. So numerically, we do see a very large overlap here. For example, for the lowest states, it can go to, for example, 0.99 above 0.99, and for some even higher states, it goes above 95%. So to quantitatively describe the quality of the conformal symmetry, we define a conformal cost function. That is to say, the average of how the measured scaling dimensions deviate from what the conformal symmetry wanted to be. For example, in this cost function, there can be the difference between the stress tensor to 3. There can be the difference between the symmetry current to 2, and there can be the deviations from of the derivatives from integer spacing. So in practice, we include or in the cost function every operator that is below 3, and optimize this Q for each system size and see how the cost function scales with the system size. We can see that for SP3 and SP4, this cost function, it goes down very quickly with the system size. Whereas system size, meaning that the conformal symmetry is getting better and better when you increase the system size. On the other hand, you can see that for the SP2 theory, which corresponds to the deconfined criticality, it doesn't go down. It doesn't go down very quickly, and we expect it to scale to some constant value, which is much larger than the SP3 and SP4, which for even at the system size, even at the finite system size.
How many parameters are you tuning? Do you know?
4 parameters. Yes.
Can I ask a question?
Yes.
It's a quick one. How do you fix the normalization of your Hamiltonian?
We optimize that as well.
The multiplicative normalization is arbitrary.
Yes, it's arbitrary.
Oh,
so we fix one of the 5 parameters and tune the other 4. Yes.
Yeah. So this 2,1 theory, it's supposed to be, which here you don't see that it's not formal. It's supposed to be somewhat similar or maybe identical to the theory which people studied using fuzzy sphere with precise SO5 invariance.
That's true. That's exactly the same model.
Exactly the same.
Yes.
But here I don't see SO5 symmetry. Is there SO5?
SO5 is SP2.
Ah, okay, so it's precisely the same model. Okay.
Yes. You can regard all these models as a generalization of the deconfined criticality.
Okay.
Yeah. So we are saying since the SP2 it corresponds to D2CP, it is supposed to be pseudo-critical or approximately conformal. So that's why we see that its cost function doesn't scale to 0.
But to get the SO5 from SP2, you have to fine-tune your parameters, right?
SO5 is SP2.
Yeah, but you
Yes, here we indeed do some fine-tuning to find the optimal conformal point. Yes?
And this is kind of away from the symmetry broken region, right?
Yes, away from symmetry broken region.
But in this sense, I mean, if it's not conformal, then it is symmetry broken.
And
So it would be on the boundary of the symmetry broken region in some sense.
Oh, you mean for the SP2 case? If you are in an ideal world, you are in the thermodynamic limit. There is nothing but a symmetry broken face. But in the finite size, you are able to stuck in vicinity of a pseudo-critical region, where it is quite close to what we conjecture to be a pair of complex fixed points, so that you can see some approximate conformal symmetry. But if you take the size to large enough, it will actually be symmetry broken. It's just the signal is not clear in small system sizes.
But here you have more coupling constants than in the first paper. Is that correct?
That's true. That's true. That's true. We are tuning more parameters to see how good we can get the conformal symmetry.
Yes. And the problem is not the optimization. There's like a unique minimum. It just has a higher value.
That's true. That's true. We seem to we find that no matter how well you tune, the minimum is still not going to 0. Yes.
Is there a regime with analytical control if n and m are large in some way, or not?
We're not considering large n and m. Yeah.
I think you need to take large K at the same time, then the gauge theory becomes under control.
In the gauge theory or in the
gauge theory, if you take large N and large K proportional to each other, then it's under control.
No.
Yeah.
Yeah. That could under control, but that's like the Tohoku limit, right? That planar limit. But if you take that
large NF, you keep SU1 or SU2, take large NF and large K, that's under control.
But not in this space of theories.
No, it is the same theory, it's just increase N and M is the number of flavors here.
For example, you can consider half filling and then take N to large. That's correspond to SU2 gauge field of n flavors of fermion.
No, but
that is control.
But these theories are all level 1.
Yeah.
You have to add another index to get higher levels.
No, for this
you can change levels.
Yeah, I think Zheng has some slides talking about those.
But can you get something interesting in 2+1 like that, or can you get to a regime where you have a controllable fixed point you can study in a control?
Not in the fuzzy field model yet, but in the field theory, yes.
In the gauge theory or in the signal model?
In the gauge theory. Not for signal.
Yeah.
I may add that it's also very intriguing if we can study the large N limit, like perturbatively on the fuzzy sphere. But this is far from knowing how to do.
For example, there was talk about OM model, right? You can just say take that OM model and make it large, whether you can really analytically control that fuzzy sphere model. That would be interesting.
But why would it be interesting? We already know how to solve that model. It's interesting when you can solve models which people cannot solve another way.
But that will give you inspiration about how to deal with this, right? Because OM is simpler, right? We know much more about it.
Not so obvious on the fuzzy sphere.
Yeah.
I mean, here everything is homogeneous. You only have SPN fundamental.
Yeah, that's a good point.
Yes. So the lesson to learn is things are hard elsewhere can be easy on fuzzy sphere. Yeah, Ellie. So we can look further at the spectrum. So here is the SP4 half field that people are wanting to see. So we can remind you that these series of models are described by the nonlinear city model on symplectic Grassmannian with a level 1 Wess-Zumino-Witten term, and there are candidate theories as Chern-Simons matter theories. So what can we see from the spectrum? First, for these different N and M, there are many operators with similar scaling dimensions. For example, the lowest SPN antisymmetric rank 2 tensor, which is supposed to be the order parameter of the symmetry broken phase. This is the lowest operator, and a rank 4 tensor, for example. But there can also be operators that doesn't exist in small n series theories. For example, this 2, 1, this SP2 theory. It is the deconfined criticality. I've been advised that not to talk about 2, 1. Would be our dream to realize that on the fuzzy sphere. Okay, so there are also operators that doesn't exist in the SP2 case, but then because this representation is not allowed, but then start to exist on higher N and M. There can also be very interestingly operators that are very high in SP4 with quarter filling. For example, this rank 4 totally antisymmetric tensor and this rank 6 tensor. It is very high in the quarter filling case, but becomes very low in the half-filled SP4 case. And we especially care about the singlets, which tells us the fate of this theory. We seem to find that in all of these theories, these singlets are very close to 3, which gives us really a hard time finding out the nature of these theories, whether it is a stable phase or a phase transition. And yes, and due to the numerical error, we are still not sure whether or not this is larger or smaller than 3.
So what is the numerical error?
And so you can have corrections from irrelevant operators.
When you put it on those numbers, where is the error? Can you say how much these numbers?
And this is difficult to estimate. In fact, I think it remains a quite open question how to rigorously estimate numerical error with exact diagonalization. And here we just want to show you qualitatively how the spectrum should look like at our best conformal point. And so if you in the half-field case, this lowest singlet is parity even, and there exists another singlet which is parity odd. This operator is quite high everywhere in the NM theory. So if you take a fermionic description, this parity odd singlet should most simply correspond to the mass term. Here it's intriguing to find that in all of these theories, the so-called mass term in the fermionic descriptions are quite highly irrelevant. And this is quite robust under the region we choose. So in the D2CP case, this tells you that it's impossible to directly flow to the corresponding liquid with an infinitesimal perturbation.
This diagram you showed, you were supposed to be able to flow to the spontaneously broken phase with the relevant perturbation, right?
Yes.
And that would be the S in this diagram. What would be the perturbation that does this? It's the singlet S.
Yes, yes.
So that's supposed to be relevant for consistency with the picture.
And it is possible that you can directly flow to the SSB, or it is also possible that there is a phase transition between this CFT and the SSB.
In any case, you need the relevant direction in order to propose phase diagrams, or not?
And if this CFT and the symmetry broken is separated by a phase transition, I don't. Yeah, because it's stable, and you have to turn on a finite amount of perturbation to go to the SSB.
And another question, so that there was some bootstrap study, I think it was mentioned something critical as a 5 fixed point. Is that supposed to match your number? Well, is that supposed to match your number? Do they have this singlet?
They are under the estimation, and they are under the assumption that there exist 2 relevant singlets.
So,
which is to say, they are under the assumption of D2CP is tricritical.
Yes, sorry. This would never correspond to a trivial point. Sure. Okay.
Yes.
So you have a case where S is indistinguishable from 3. Do you ever see a phenomenology which looks like within the variable sizes looks like a fixed line?
We seem to see that on the other side of this CFT there exists a symmetry breaking region, but it's very surprising that here diagnosing the CFT is much easier than diagnosing the stable phases. So maybe in the future we are able to construct these topological orders explicitly and explicitly study these transitions, so that we do not have to make use of the nonlinear system model, which is unclear to us which transition it is. Yeah, I therefore encourage the organizers to organize another of this conference next year, so that I can talk about these progress.
No, but I think Adam meant something different. He meant, okay, if there's an operator which is almost marginal.
Yes.
Then you should see that when you perturb your theory a little bit, the spectrum basically remains conformal.
We do see that this spectrum remains conformal in a relatively large region.
Let me add something. So
yes.
At the beginning, Zheng just tried 1 parameter tuning. That's just like VOU, like our original DQCP paper. Yeah. And for that computation, there is a very large window showing almost a conformal behavior. Here, he's doing like more parameter tuning just to get the conformality value.
Well, almost conformal in that window, but with different deltas?
Yeah, that shift a little bit. Right?
Okay.
Yeah.
Mm-hmm. I also have another question. So,
yes.
You discussed what would it take to perturb this theory and flow to the broken phase. But I think by the logic of your talk, you expect that this CFT that you find, at least you would like to interpret it as the infrared fixed point of a gauge theory.
Yes, so here we list several possible candidates
that the CFT could correspond to.
Okay, so there is some gauge theory. That's your working assumption. Or you would like to interpret this way. Now, if it is an infrared fixed point, then they cannot be relevant singlets.
That's true. We still don't know from our numerics either whether or not there are.
Well, you have there, I mean, S is 2.979.
It's very close to 3, and we are still not able to judge whether or not it's.
Let me add this. So for those gauge theories, if let's say the flavor is very large, it's semi-classical, we know that there will be 1 relevant singlet. But when you here we're dealing with very small flavors, we don't really know what's the corrections come from the interactions.
No, I'm just saying that if there is an RG flow, which flows from the UV to IR fixed point, if such a flow exists, and if you don't tune anything additionally, they cannot be relevant singlets. It's a very basic fact.
Right, right.
So, yeah, well, anyway, so that S better get irrelevant with some more precision, otherwise there's a problem here somewhere.
Thank you for the comment. Max?
So sorry if I missed this, but in the cases when you don't have particle hole symmetry, how do you tune to this line between the SPM and the SPM minus M?
So far, we cannot distinguish whether or not what corresponds to this theory that we find, and I think to distinguish these two, I think you need more evidence from the topological order in vicinity.
No, but even in the theoretical scenario, that would be the M psi bar psi operator that tunes you.
Yes.
But you are finding that that operator is.
That means that this could expand into a region. But if you hit large enough finite psi bar psi, you could still be able to get to these topological orders.
So it could actually be a region.
Yes, it is a theoretical possibility.
And your numeric seems to be.
Yes, if these theories we find correspond to the fermionic theory. Yes, and we're pretty confident that this S minus is irrelevant.
And do you know that these theories that you find that they are not endpoints of the SSB phase? That is not this trajectory.
The endpoint, the trickle point, yeah. that would require at least 2 relevant singlets, which is highly unlikely here.
Yes.
If S really is slightly less than 3 and so close to 3, then it should have a short RG flow when you turn on S, which you could probably compute perturbatively in terms of this data.
But distinguishing that could be difficult, because actually with so many flavors, we actually have a quite small system size we can access.
That's maybe related to my question, that the tri-critical point and the critical point could be very close together somehow in scaling dimension space.
Yes.
Will you say more about the gauge theory candidates? Because do you want to say this 4-2 theory is 2 colors of gluons in 3 dimensions with 4 flavors of fermions? Is that
that's true. That's the most plausible possibility.
And these fermions are in a fundamental representation of SU2 color?
Yes, yes.
And they have a spontaneous symmetry breaking SP4 to SP2 times SP2?
Yes, that's on the other side.
Okay.
What is one question?
Thank you. What is the gauge theory description of the parity even single?
So that's supposed to have a conformal.
So for the fermionic description, it would at least be 4 fermion operators.
Okay, we should probably keep these.
Yeah. Yeah. Shall I move on? Yeah. So far, I've promised you that this model on the fuzzy sphere realizes the nonlinear system model with Wess-Zumino-Witten level 1. But how exactly is that true? We want to look more carefully into that in theory. So brief recap. A Grassmannian of the group either SP, U, or SO can be parametrized by a n by n matrix, which is formed by interacting by acting the group element on a reference matrix, which has M1 and n minus M minus 1. So in terms of this matrix field, you can construct a nonlinear system model with the kinetic term. And when the pi4 group of this Grassmannian is non-trivial, it admits a Wess-Zumino-Witten term, which can be written extending to the fourth dimension. And it is an integral of a four form on the extended space, so that it is topological and doesn't couple to the metric. So we have seen that it can correspond to various critical gauge theories. For example, for the U group, it can have the candidates as various Chern-Simons matter theories with fermionic or bosonic matter, and the same thing happens for a general level K symplectic model and the orthogonal model. So that is the step from the nonlinear system model to the critical gauge theory. Yes. Oh, sorry. Then critical gauge theories. We still need to go. We still need to go from fuzzy sphere to the nonlinear system model. So how exactly do we know that the fuzzy sphere model corresponds to a nonlinear system model with a certain Wess-Zumino-Witten term? So to do this, we start from a free fermion theory on the lowest Landau level, and then we couple them to a matrix field on the Grassmannian. And this coupling essentially, if you integrate out Q, it essentially describes some kind of four fermion interactions. But instead, you could integrate out the fermions, and you obtain some kind of effective action of the matrix field Q. And in order to do perturbative calculations, we expand Q into this reference matrix sigma with a perturbation delta Q. So this perturbation to the second order, it can give the self energy correction to the nonlinear to the matrix field Q. But in the fourth order, this box diagram in return gives you the Wess-Zumino-Witten term that you desire in the infrared limit. That is to say, all the momentums here goes to approaches 0, and we can do this calculation explicitly on any Grassmannian that we want. And for the SPN Grassmannian that we have studied in detail before, this calculation tells you that its Wess-Zumino-Witten level is 1. And you can do the same calculation, for example, on the UN Grassmannian with n flavors of fundamental fermion. And this calculation will also tell you that it has a Wess-Zumino-Witten level 1. However, there's an extra issue with the U Grassmannian. The SU gauge theories are much more complicated than the SP, even if the SP is not familiar to many people. There's an extra that there is an extra issue of the Sturmian U1 symmetry. So when the pi2 group of this Grassmannian is non-trivial, this theory admits an extra U1 symmetry, and all of its IR fates also have this U1 symmetry. And in the fuzzy sphere model, it is implemented as the charge U1 symmetry, which causes a problem. That is to say, it always have to be gapped out because the charge sector always need to be separated from the spin sector, so that with this setup, one can never realize any. With this setup, one can never realize any theories that critical theories that the U Grassmannian with Wess-Zumino-Witten level 1 can correspond to, because in those critical theories, this U1 have to be gapless, whereas on fuzzy sphere, it have to be gapped. So
Can you say again, this field Q, where does it take values?
in the Grassmannian, which is parametrized as a, I can show you again. Yes. Okay. Yes.
When you integrate over Q, do you get exactly this V interaction that you had, or?
Here I'm just constructing the simplest model, and there's no guarantee that what kind of four-fermion interaction I get.
So it's not strictly speaking like a Haber-Sazonowicz decoupling of the...
Not strictly speaking. I just want to construct something that looks very similar to what we have in the Hamiltonian.
So in the U1 and the U4 model, I guess you could imagine tuning some coupling to make the U1 critical. And then you would get a different CFT. Is that something you could look at?
I would say this is never possible for two reasons. And the first is that the U theories with Wess-Zumino-Witten level 1, it always has to have fermionic operator content. And on the
what's wrong with that?
On the fuzzy sphere, on the other hand, if you want to have gapped charge degree of freedom, you can I'm
suggesting that you study a model where you have a gapless charge degree of freedom. That would actually be related to this superconducting critical point that I talked about.
Thank you for suggesting that. Maybe a direction of study, but
I think just by translational symmetry, charge cannot be part of your, like, microscopic charge cannot be part of your CFT because you have a magnetic field. Because of the translational symmetry is projected.
Yeah. Okay. But it's not contributing to the Wess-Zumino-Witten term. It has no anomaly of its own, I think.
Yeah. So besides that, we also have an alternative approach. That is to say, we can engineer the Wess-Zumino-Witten level. For example, if you take some simple transformations to the model, for example, take its complex conjugate, you will not change the Wess-Zumino-Witten level. If you take the particle Hall transformation, you will inverse the Wess-Zumino-Witten level. On the other hand, if you do a stacking, for example, you consider two copies of some system, you will add up the Wess-Zumino-Witten level. This can give us a hope to study some kind of theories. For example, the U Grassmannian with Wess-Zumino-Witten level 2. With Wess-Zumino-Witten level 2. And the setup is like we consider n flavor of fundamental fermion and n flavor of anti-fundamental fermion. So that stacking them up, we can have a superposed Wess-Zumino-Witten level. That's level 2. On the other hand, the Sturmian U1 that we are dealing with previously is now implemented as the relative charge of the first n flavor and the second n flavor, so that this can actually be gapless. And this theory has no issue that we have mentioned before. And this theory has the candidates of n flavor of boson coupled to UM or UM n-M level 2 or minus 2, and SU2 coupled to n flavors of fermion, or n flavors of fundamental fermions.
Okay, you are at time. So
Okay. I will do a brief summary. Yeah. So in this talk, we have shown how the nonlinear signal model can bridge us between fuzzy sphere and the critical theories. And as a concrete example, I have presented that we have discovered a series of symplectic CFTs described by the nonlinear signal model with Wess-Zumino-Witten term. I have presented numerical evidence for the conformal symmetry and discussed about the operator spectrum. And their candidate theories can be some Chern-Simons metric theories. And more generally, we have shown how fuzzy sphere can be matched with the nonlinear setting model, and how the nonlinear setting model can be matched with the critical gauge theories. And what are the future? So we want to study some other Grassmannians, for example, the Grassmannian of U or SO, or even the Grassmannian of SU, which will be much more complicated, and other Wess-Zumino-Witten levels. Can we do anything without the bridge of nonlinear setting model? For example, can we study directly the Chern-Simons matter theory and Chern-Simons matter theories by matching, for example, the phase diagram or some pattern construction? Can we realize the direct spin liquid that people want the most? And another technical problem we want to ask is what is the systematic approach to unknown CFTs on the fuzzy sphere? So this talk is based on this paper in collaboration with my supervisor, Chen He. And I want to briefly show you some of the results of the fuzzy sphere that is not mentioned in this conference. So we can realize the defects and defects changing operators as mentioned by Max on the fuzzy sphere, and we can measure their scaling dimensions by state of correspondence, and more importantly, we can measure the G function by taking overlaps, and we have collected many results, and we have shown that for defect and also for boundary. And we have shown that the conformal perturbation theory actually helps a lot in improving the quality of the multiplate in the conformal boundaries. And you can study conformal boundaries without realizing them by taking the overlap of a bulk CFT with a polarized state. And there is a very cool package, FuzzifiED, that helps everyone to do numerics easily on the fuzzy sphere. Yeah. Today is today is actually a special day of one year anniversary of this package.
More questions?
So how do you define the anniversary, the birth of the concept?
So one year before that, we have sent out widely the emails to.
So that's the date of the birth. just to know.
That's celebrate the art.
Yes. I don't know. You forgot. You don't even know when it was born.
It's too late. Still late.
Yes.
Oh yes.
So I'm still intrigued by your conjecture that you are dealing with, if I understand correctly, 3D QCD with 2 colors and 4 flavors, right, of fermions. Is that right?
4 2-component flavors.
I would say two flavors.
Four flavors.
Yeah.
4 flavors. They transform in the doublet representation of SU2.
Yes.
And of course, since we are in 3D, we have no chiral symmetry, no left and right.
True.
So what are these fermions? Are they some kind of marijuana, or how should I think about this? And what is the two-component fermions, and they have a certain flavor symmetry.
Yeah.
Yes. And that is SP4?
Yes, they transform in the fundamental of SP4.
Yes.
No, I think he's referring to the fermions on the fuzzy sphere. I think you're talking about the fermions in the gauge theory.
Yes, exactly. I want to understand.
His fermions are gauge neutral.
Yeah.
Your fermions are not. Those are different fermions.
Yeah. So that's why I'm asking again. So what gauge theory do you think you have captured in your fuzzy sphere calculation?
Yeah.
Maybe you should show the slide that you had a table of these things.
Yeah. Maybe let's just consider one case.
Yeah. So in the half-field case, this Chern-Simons level goes away, and it's the SU2 gauge field coupled to n flavors of fermions, and transforming in the fundamental representation of the SPN flavor symmetry of the gauge non-invariant fermions, and they are like pseudo-real fermions, or direct.
The gauge group is SU2 color.
Yes, and it is also transforming in the fundamental of the SU2 color.
Okay, yeah. And so there is a flavor symmetry which is SP4. And what is the significance of the subgroup SP2 times SP2?
So that it can offer a symmetry breaking pattern that this QCD can go to.
Of course, from 4 dimensions we are used to SU2 left times SU2 right, but here, where does the breaking into 2 segments come from?
So the thing is, when every fermion gets gapped out, it introduces a Chern-Simons level half. And if you gap out the 4 flavors, you need to make sure that these 4 flavors, the consequent theory is Chern-Simons neutral. So you have to gap 2 flavors from one direction and the other 2 from the other direction. So that comes the symmetry breaking.
So I guess the question is how do you realize the broken phase in the gauge theory? What would you need to do with the gauge theory to see this broken phase? That's the question.
It will need to couple to a mass field.
No, but that's explicit breaking.
You fall from your own.
Yeah, with some full fermion term, drive it at strong interaction.
Relatedly, could you say something about the extremes of the phase diagram of the model you're actually studying?
The extremes?
Yeah, what are the phases far away from the dangerous region?
Yeah. So, so in the small v limit, that is to say dominated by the u, it is symmetry broken. This we know very clearly. And if you add a little bit of v, it will set the symmetry broken to SPN. So with small v, it is symmetry broken of SPN. And with large v...
So you said SPN down to what? It's completely broken? No.
SPN down to SPM times SPM minus m. That is the symmetry breaking pattern described by the Grassmannian. And in the large V limit, it is unclear. We still seem to see a little bit of signature of conformal symmetry.
And so how do you know about the number of colors? I guess you know that your fermions should sit in a pseudo-real representation of a gauge group, whatever the gauge group may be, and then SU2 is the simplest guess.
From the Wess-Zumino-Witten level. So the Wess-Zumino-Witten level tells you what the gauge group should be.
I see.
Okay. So
maybe I didn't understand something. So you had in the FuzzifiED, what was the significance of that field Q in the model? You had the matrix. Was that another field or was it fixed?
This is to try to write down the effective model of the FuzzifiED model in terms of the nonlinear sigma model. So it's like a not so serious version of Hubbard-Stratonovich transformation.
So was that another field on that you include on?
No, we don't simulate them. We just try. This just tries to help us understand the theory.
So at zero mass, is there a parity operator? Is parity conserved when you go to the zero mass of the fermions? Do you think? In this gauge theory you're talking about,
yes.
When you go to zero mass, there's no chiral symmetry, but you get parity symmetry when you go to the critical point of zero mass.
Well, when m equals half n, there is parity symmetry. In general case, there's no parity symmetry.
No, I'm talking about this case when it's even, yeah.
Yes.
And then you'll get parity symmetry at the critical point.
Yes, and it is realized in the microscopy model, so we're pretty sure.
Oh, okay, good. Yeah, okay.
Okay, I think we should continue discussions after this session. Thank you.